Hello everyone. In this video we are going to talk about what we call rigid body motion, which includes translation and rotation. So in the previous videos all we talked about was rotation in one place, and we showed that you can show this rotation by a rotation matrix, by Euler angles, axis angle representation, and unit quaternions. Now here, in real life, the rigid body does move, does translate and rotate. So if we want to combine them into the matrix format, how do we do it? And this needs something called homogeneous transformation matrix and homogeneous coordinates. So what does that mean? In general, if I have a point, in one frame, and I want to show it in the other frame, depending on how those two frames are situated with respect to each other, I can have different ways to show it, right? So let's say here I have this frame 1 and frame 2, or frame 0 and frame 1 you might call it. So let's say this is x0, y0, and z0. And then you also have frame x1, z1, and y1, where the frame 1 is exactly like frame 0, except, so the orientation of the axis is perfectly the same, except you have some displacement of the origin. So if this is O and this is O, what you have is a displacement between the origins, and we can show this displacement by the vector d of 1 with respect to 0. So this is the displacement of the origin of coordinates frame 1 with respect to origin of coordinate frame 0. So now, clearly, if I have some vector p in the space, and so this is p in frame 1, this is p in frame 0, you clearly see that p in frame 0 is going to be what? P in frame 1 plus d of 1 with respect to 0. So if you write them as vectors, you can simply add the coordinate in frame 1 with the displacement of origin of 1 with respect to 0 to get what? Coordinate of the point in frame 0. It's just a simple vector addition, right? No big deal. Now, this is for translation only. We also learned that in case that we have this frame 1 at the same origin that you have frame 0, right? So the origin is the same, but the x's are displaced. So let's say here, instead, I have this x1, let's say this y1, and this z1. If I want to describe the coordinate of point P in this frame 1, what we learned in the previous lectures is P of 0 was the rotation matrix of R1 with respect to 0 times P of 1, right? So this is what we learned. Now, the question is, what if both of this is happening at the same time? Then all you need is to combine them. So first, you rotate the coordinates of P in 1 by the rotation matrix to align it with frame 0, and then add the displacement between the two origins to it, and this is what you will get. Okay, and this is what we call the rigid transformation. So in this case, your frame 1 is something like this. The origins are not the same, the orientations of the axes are not the same. And you can describe coordinate of P in both of these frames, which is really good. Okay? So it involves a product and a vector addition. Good? So now, again, we call it rigid body motion. The question is, if I have more than one of these, then what? Correct? So basically, I go from frame 0 to frame 1, frame 1 to frame 2, and so on. Let's say for now, just say we have frame 0, 1, and 2. Then I can write that P of 0 is R1 with respect to 0, P of 1 plus D of 1 with respect to 0. then I can say P of 1 is R of 2 with respect to 1, P of 2 plus D of 2 with respect to 1. Yes? So these are the two rigid body motions from 0 to 1 and then from 1 to 2. Now, can I replace them with one single relation that directly takes me from 2 back to 0? So can I write it with something like this? R to 0 of P2 plus D to 0. The question is, what is D to 0? What is R to 0 in terms of these other rotation matrices and the displacements? Right? So here I'm trying to find the equivalent of two rigid body motions or two rigid body transformations. How can I do that? Well, all you need is to replace this bottom relation that has P1 right into the top equation. If you do that, you'll see that P0 is going to be R10 times R21, P2 plus D21, and then plus the whole thing added to D10, which if you expand it, it will be R10, R21 times P2, and then plus R10 times D21 plus D10. And now if you compare it, you clearly see that R2 with respect to 0 is the product of the two R's, pre-multiplication, which is what we expected. Remember, if we had only rotation in place, and it was with respect to the current axis, we did pre-multiply, so this is exactly meaningful. The problem comes here with this displacement vector. The displacement vector of d of 2 with respect to 0 is not simply addition of d of 1 with respect to 0 and d of 2 with respect to 1. You have to multiply this rotation matrix by d of 2 with respect to 1 to get d of 2 with respect to 0. And this is quite meaningful. Why? Because if you look here, I cannot add these two vectors, these two d vectors together. Why is it? Remember, I told you anytime you want to do arithmetic on the vectors, all of the vectors have to be written in the same frame. Right now, your D1, 0 is written in frame 0, D2, 1 is written in frame 1. The references are not the same. I cannot add them together. If I want to add them, they both better be written in the same frame, let's say frame 0. Why 0? Because here I want the result to be with respect to 0. So this guy, this d of 2, 1, I have to somehow project it and write it in frame 0. And you know, if I have any vector in frame 1 and I want to take it to frame 0, I need to what? Multiply it by r of 1 with respect to 0. So this is what? This is projecting this vector back to frame 0. Okay, this is alignment or projection. Then you can add it to this guy, which is now written in the same frame. Okay, so that's r of 2, 0. This is d of 2, 0 as a result of the rest of them. And the problem becomes more and more complicated. This formula gets bigger and bigger when you have more and more rotations. So in general, you can show that the relation is going to be recursive like this. The rotation part of it is not too hard. It's just the product of all rotations in a pre-multiplication way, okay, from left to right. So that's not a big deal. The only important thing is the translation relation. That is going to be now a recursive formula. And it gets bigger and bigger, okay? So if you have, for example, let's say 4 rotations, your R of 4 consecutive rotations with respect to a previous one or current one, R40 is going to be what? R going to be the product of 3 R's. So this is 4, 3 multiplied by 3, 2, 2, 1, and 1, 0. So that's not too bad, but D40 is going to be something times D43 plus another something times D32 plus another something times D21 and finally plus D1 with respect to 0. Okay, now what are these? This is written in frame 1, but everything has to be in frame 0. So this has to be rotation matrix of 1 with respect to 0. This has to be, since this is in frame 2, it has to be rotation of 2 with respect to 0. This has to be rotation of 3 with respect to 0. But I don't have this one and this one. So instead of that, I have to write it as what? Or this one. I have to write this as R01, R21. And this guy is going to be R what? 32, R21. Sorry, backwards. R10, R21, R32. So you see, each time I want to take one of the new displacements and add them to the rest of it, I have to keep multiplying by lots of rotation matrices to project them back into frame 0, so now I can add them together. And as I said, this formula gets bigger, and plus, this formula that you see here is not a simple product anymore. You have to now add something to the product. So the question is, can I change this formula that P of 0 is R of 10 P1 plus D10? Instead of writing it as a product and an addition, can I just write it as a simple product? So here I multiply P1 by something, no addition, I just multiply it by something, and when I multiply it by something, the effect of it will be like what? Will be like I'm doing the whole rigid body motion. So we say yes, it is possible, and we call that matrix H. We call it homogeneous transformation matrix. But the problem is this: since that one is going to include both rotation and translation, and the dimensions of P0 and P1 are 3 by 1. What I need when I want to combine these is to bring in or augment an extra 1 to the P0 and P1. So instead of these coordinates for P0 and P1, I'm going to add a 1 at the bottom of these vectors. So I define a new P0. This is like the P0, whatever it was, plus 1 extra 1. So if this guy has an X component, a Y component, and a Z component, at the bottom of those 3 components, you will add an extra 1. So this is a 3 by 1. This new guy is a 4 by 1. The same thing I do to the P1. So P1 prime is going to be whatever P1 was and an extra 1. Again, this is a 3 by 1. This new guy is a 4 by 1. And now, if I want, I can write this P0 prime in terms of P1 prime, where now the dimensions are 4 by 1, and this matrix is going to be a 4 by 4. And I can show you that that matrix now can easily include both rotation and translation. So first of all, this new coordinate that I defined for the points where I augmented them by a 1, we call them homogeneous coordinates. These are the homogeneous coordinates for P1 and P0. And this matrix, we call it what? We call it the homogeneous transformation matrix. Okay, if you want, you can add the word transformation. Now, what does this H include? You can show that H is simply of a form what? It has this 3 by 3 portion of it to be your R matrix. This 3 by 1 portion of it to be your D vector. Then here you have 3 zeros and you have a 1. Okay, so remember the dimension of this guy is a 3 by 1. This is a 3 by 3. So when you put them next to each other, it's going to be a 3 by 4, and then you add an extra row, so it becomes a 4 by 4. And it's not hard to show that when you multiply this by P1 and 1, what happens? When I multiply that, I will get this R to be multiplied by P1 and added to D1 0. And here I will get, if I call this whole thing vector 0. This vector 0 is multiplied by P, which is 0, and 1 times 1, which is going to be a 1. And then I call the result of this what? P0 and 1. And of course, 1 and 1 are equal, and P0 is equal to what? R1 0, P1 plus D1 0. So by adding this extra 1, it is possible to convert your relation that has a product and an addition into one simple product, but just you need to augment a 1 to your coordinates, and your transformation matrix is now going to be a 4 by 4. But the form of it is going to be RD, 3 zeros and a 1, which you can also see here. Okay, so here you see this this bold font 0, it means a vector of 1 and 3, right? So 3 zeros. And as I said, now you call it H, and since this H takes you from frame 1 to frame 0, you also give it sub and superscript, and you call it what? H of 1 with respect to 0. So what does H of 1 with respect to 0 do? It takes P1 back to P0, considering that it can do both rotation and translation, and this is making life very easy. So now if I have two rigid body transformations right after each other, I do not need to go and use these formulas that I had here. You see here, I had 4 rotations and translations, and these were the formulas that I used. And as I said, the D formula especially gets bigger and bigger. Instead of that, all you need to show is to say P0 is equal to H4 with respect to 0 times P1, where this H of 4 with respect to 0 is simply H of 1 with respect to 0, H of 2 with respect to 1, H of 3 with respect to 2, H of 4 with respect to 3. So the same way that you did composition of rotation matrices, now you can also combine these homogeneous matrices. And that is very convenient. Okay, so you can combine them. Now, before we get into any other thing about their inverse and everything, let's take a look at some of the fundamental homogeneous transformation matrices. For example, let's say the rigid body motion that this H represents is only what? Pure translation along the x-axis, no rotation at all, just moving something along the x-axis. Well, if there is no rotation, it means the rotation matrix has to be the identity matrix, as you can see. And all you have here, if you look at your D vector, so this is your R, this is your D. If you see D, it only has A for X, 0 for Y, 0 for Z. So all this guy does, the last row is always constant, okay? The components of the last row never change. They're always 3 zeros and a 1. It's the first 3 rows that you change. But the first 3 by 3, which is R, is identity because there is no rotation, and then you have A for X. So this is what we call translation of X and A. Similarly, translation of Y and B, again, identity matrix for R. The D vector has B in Y, and similarly, you have translation of Z and C, as you can see. Now, if I have a pure rotation about the x-axis, no translation whatsoever, right? No translation whatsoever, just pure rotation angle alpha x. Then your translation vector is pure 0, and your rotation matrix is what? An x rotation matrix, which we had in the past. Similarly, if it's pure rotation y, again, translation is 0, your rotation looks like a y rotation. And the same thing for z rotation, again, translation is 0. Now you might say, what if I have like a translation x and a rotation z? Well, you just combine. So you have this rotation z, so you have this guy at that 3 by 3, and you also have this one in what? In translation x, right? Correct? So you can just, by putting proper displacement vector and the proper rotation matrix, these are the very basic fundamentals. You can have any combination of them. So this is very important to understand how you form the fundamental H matrices. And to understand it a little bit better, I'm going to solve an example first, and then I go back talk about the inverse and everything. So first, let's do an example. So here, what I have is a block on a table. The block has this coordinate x to y to z to attach to it. I have this robotic manipulator. It has 3 degrees of freedom, all revolute joints. And the base of it is x naught, y naught, z naught. I have also a coordinate frame at the corner of the table, x1, z1, y1, which is attached to the table. And I also have a camera here at the top that the coordinate attached to that camera is called x3, y3, and z3. The dimensions here are given, okay? From the base of the robot to the table, the dimensions of the table, the block is at the center of the table, and then the offset of the camera from the table. What you want to do is to find the homogeneous transformation of frame 3 with respect to frame 0, which is the camera with respect to the base of the robot. So the question asks, what is h of 3 with respect to 0? Once I know that, that's just enough to do it. So I can just attack it all at once, or say, well, it's better for me to first go from 0 to 1, then go from 1 to 2, then go from 2 to 3. You don't have to, but I just, for the sake of practice, so we just consider it in steps. So if I find each one of these h's, multiply them together, that gives me the final result. So what is h of 1 with respect to 0? Well, it is like r of 1 with respect to 0, d of 1 with respect to 0, 3 zeros and a 1. Where what is r of 1 with respect to 0? R of 1 with respect to 0 means how the axes of 1 are oriented with respect to the axis of 0. If you look at them, they are exactly the same x, the same y, the same z. So there is no rotation from 0 to 1. So the rotation matrix is simply going to be the identity matrix. What about displacement? When I go from origin of 0 to origin of 1, what is my displacement vector? This guy. Whatever it is, it has to be calculated or projected along which frame? Along frame 0. In other words, how many units along x naught, how many units along y naught, how many units along z naught I should move to go from the beginning of the vector to the end of the vector. And you clearly see that I need to move 1 unit along y, 1 unit along z, and since the origin of here and that corner are on the same x value, on the same zy plane basically, there is no change in x. So the displacement that I need is no x, but 1 y and 1 z. That's enough to take me from origin 0 to origin 1. Okay, so that's h10, done. Right? Good. Now let's go and look at h21. So this is R of 2 with respect to 1, D of 2 with respect to 1, 3 zeros and a 1. Where what's the rotation of frame 2 with respect to frame 1? If you look at the orientations, again, the orientations are the same. Z's are in the same direction, Y's and X's. So again, there is no rotation involved, so I can say that all I need is an identity matrix. What about displacement when you go from origin 1 to origin 2? How many x1, how many y1, how many z1 units do you move to go there? Well, if that's in the center of the table along y, you move half of the width, which is half a meter. You don't go up in the z, they are on the same xy plane. And in the x, you go backwards half a meter. So x is negative 0.5, y is positive 0.5, and z is 0. Correct? That is h of 2 with respect to 1. And finally, what is h of 3 with respect to 2? So R32, D32, 0, 0, 0, 1. Let's see if we can find this one. So now we go from 2 to 3. So first let's look at the displacement. What is the displacement? So you go from here to here. How many x2s, how many y2s, how many z2s do you go to get from origin 2 to origin 3? Clearly you see it's right above it. So there is no x or y displacement. All you have is z, and the displacement is 2. So it is going to be 0, 0, 2. As simple as that. Right? That's your z. Now the question is, what is the rotation matrix? So can I form the rotation here by a simple rotation about x, y, or z? Then it's going to be one of the fundamental matrices. So if I clearly you see the x's are different. If I rotate about x2, can I make sure that I get to the next one? No. Why? Because x2 and x3 are not the same, so it means that you cannot keep x2 constant and rotate about x2. That's not going to happen. What about y2 and y3? Are they the same? No. So it's not a rotation about y2. What about z2 and z3? Are they the same? And the answer is no. Although they are along the same line, but their direction is different, up and down. They have to be exactly the same. If two of the axes are staying exactly the same, then the rotation is about that axis. But here you see none of the axes is perfectly the same as the previous one. From 3s and 2s. They are not the same. So it's not a single or a simple x or y or z rotation. Now you can try to figure out what combination of those x, y, z would make this happen. Yes, you can do that, but what I would say always is, it's always better to go back to the definition of the rotation matrix. If you remember, this was what? Each column of it was one of the new unit vectors described or projected along one of the old ones. So for example, this x3 is going to be dotted with x2, is going to be dotted with y2, and it is going to be dotted with z2. Right? It means the first column is simply the projection of x3 along frame 2. Then you do a similar thing for y3, and then you do a similar thing for z3. Right? So let's see if I can do it. So if I want to write this x3 along the axis of the old frame, How many components does it have along each one? Well, you see it exactly matches y2 and is perpendicular to the others. So it does not have any x2, it does not have any z2. All it has is completely one full component along y2, and that's it. Done. Then we go look at your y3. Does y3 match any of those? Yes, it perfectly matches x2. So y3 is only x2, no y2, no z2. y3 is pure x2. It's perpendicular to the other twos. And finally, what is z3? z3 is in the same line with z2, but opposite of that, and perpendicular to x2 and y2. So no x2, no y2, since they are in the opposite direction, the dot product becomes -1. And you clearly see here, this is not the form of any of those regular rotation matrices. So let's go ahead and add it here, right? So it is 0, 1, 0, 1, 0, 0, 0, 0, -1. And that's it. I could capture all of the translations and rotations as you go from one frame to the next. And now all that is left for me is to multiply these three guys together, right? And I can do it by hand, or I can do it with MATLAB, right? So here I would prefer do it with MATLAB. So H1 or H10 is, it was the identity, and the displacement was 0, 1, 1. Here. So that's H of 1, 0. Then I can go H of 2, 1. Again, it was identity matrix. The displacement was -0.5 and 0.5. Now, it doesn't look like I did it correctly. No, it's the X and the Y, not the Z. So always pay attention to what you're doing. It's this guy. This is -0.5. This is 0.5. And this is 0. As I said, never suppress the output. Make sure you watch your outputs and make sure they are exactly what you wanted. And finally, your H32 is the Z displacement is 2. So this has to be 0, this has to be 0, and this has to be 2. But the rotation matrix is 0, 1, 0, like that. Then it's 1, 0, 0. And finally, 0, 0, -1. So it should be like this, and if you look at it, that should match my result here. And now I say, what is H10 times H21 times H32? And that's the result. So if we write it down, 0, 1, 0, zero, 1, 0, the displacement was -0.5, -0.5, then it was 1.5 and 3. And we had 1, 0, 0. 1, 0, 0, and 0, 0, -1. So this tells me the homogeneous transformation or rigid body transformation from frame 0 to frame 3 or 3 with respect to 0. Now, does that make any sense? Yes. Well, as you know, this guy here is my R of 3 with respect to 0, and this one here is D of 3 with respect to 0. Let's see if they make physical sense. So D of 3 with respect to 0 is negative 0.5, 1.5, and 3. What's the meaning of that? It means that if you're going to go from origin of 0 to origin of 3 directly like this, how many x naught, how many y naught, how many z naught units should you travel? It says along the x, you go half a unit. So from here, which is also the same as here, you come to the middle of this table. The middle of this table is half a unit in the x direction backward. You have to move 1.5 unit y, which is exactly here. If you look, right? This is half a unit. This is 1 unit. So it's 1.5 y, negative z. And then for z, you go up how much? This much, which is 1 plus 2. So you clearly see negative 0.5, 1.5, and 3 does make absolute sense. And then it says, how would you orient the XYZ axis of frame 3? So this guy here is x of 3, written in frame 0. This is y of 3, written in frame 0. And this is z of 3, written in frame 0. So it says x of 3 is the same as what? 1, 0, 1, 0, which means y0. So x3 and y0 should be the same direction, and you see they are. It says y3 should be the same as x0, and again, you see that they are. And it says z3 is negative of z0, and again, you see they are. Right? So you see, I perfectly described the orientation and the displacement of going from frame 0 to frame 3. So now, if this camera observes something, so if this camera observes that this block is now gone to here, and it can detect and find this distance, then you can transfer this P, where the block is, you know, the camera can tell you really x2 and y2. That's all it can tell you. It cannot tell you depth, because it's a regular camera, not a laser camera, not like a LiDAR or something. But here, you can keep the Z2 with respect to 3 constant at 2 meters. So using the camera and using this distance of 2 meters, you should be able to detect the location of P in frame with respect to frame 3 at any point. So you should be able to get this with your camera. Now you want to tell your robot end effector, let's say here you have a gripper. You want to tell this gripper, hey gripper, the block is there. I can detect it in that location on the table. Go ahead and grab it for me. Well, you cannot tell the end effector to go to this location, because this is how the camera perceives the particle to be, not how the robot should perceive it. So I need to transform this point P3 that the camera can see back and tell it in frame 0. And that's where I say P0, the coordinate of that block with respect to the base of the robot, is what? H30, which we just found, times P3. Okay, so this comes from the camera. This comes from what? This comes from how the robot is, or where the robot is with respect to the camera. So it depends on the installation of the camera with respect to base. So that can be fixed. If you don't move your camera, since the base of the robot is fixed, if you don't move your camera, don't do pan and tilt, then this is going to be fixed. This you can detect from the camera, so you can get this guy. And now that the robot knows where the block is, it can command its end effector to go there and grab it. How? I'll show you. It's our next video's topic. It's called forward kinematics. If I know the angles of each joint of the robot, how can I determine the location of the end effector based on those angles and based on the geometry of the robot? That task is called forward kinematics. We do it once we know it. Then the robot can command the gripper to go exactly where the block is, grab it, and bring it. Okay, so you see this transformation is very important. I'm trying to convey my information from a sensor to an actuator. And since they are not all in the same orientation and location, I need to go from one frame to another. And I'll do it by combining rotations and translations all in a single matrix called homogeneous matrix. So it's quite clear what I'm doing and why I'm doing it. Good. So now that we got all this, the last thing we need to talk about is the inverse of homogeneous. Okay, if you remember from the past, if I had a rotation matrix that like R10 that took me from frame 1 back to frame 0, if I wanted to do the opposite, so if I wanted to go from frame 0 to frame 1, then I multiplied by R01, and if you remember, this R01 was what? The inverse of R10, and these R matrices were what? Orthonormal, so their inverse was the same as their transpose. Okay, so since R matrices were orthonormal, instead of inverse, I could do what? A transpose, and that would make life very easy for me. So if I know 1 for the reverse of it, I could just, for the opposite operation, I could just use the transpose of it. Good? Now what about H's? So if I can go from P0 or P1 to P0 using H10, correct? Now if I want to do the opposite, so I go from P0 to P1 with H01, where H01 and H10, they include rotation and translation. The question is, what relation exists between these two guys? Are they also transpose of each other? And the answer is no, they're not. Well, because this matrix H is not just R. You remember, it's only R that is orthonormal. D is not bound to anything in R. This is a complete different thing. So your H matrix is absolutely, there is no reason for it to be orthonormal, even orthogonal. Forget about orthonormal. So because this D can be any arbitrary magnitude in any arbitrary direction, it makes the whole H matrix to not be orthonormal, not orthogonal, not normal, nothing. So no, the inverse of it is not going to be the transpose. So yes, here I can say that H01 is the inverse of H10, but not the transpose of it. They are inverse of each other. But how would you invert a matrix that looks like this? R10, D10, 0, 0, 0, 1. How would you invert it? Based on the R and D, how can you invert it? And the answer is, based on linear algebra, it's not so hard to show that. What you need is, the inverse is going to be the transpose of R matrix for the rotation part of it, but the D part of it is different. It is negative R transpose times D. Okay, so if I go back here, what relation exists? If this is H1, H01, then what is H01? It is going to be the transpose of this guy. This portion of it is like orthonormal, but D is different. It's going to be negative R10 transpose times D10. 0, 0, 0, 1. In other words, this is your R01, and you know R01 and R10 are transpose of each other. This guy here is your D01. So D01 and D10 are not just like transpose. First of all, they cannot be transpose because dimension of both of them has to be 3 by 1. And it's, as you can see, you have to add this negative R transpose to make it happen. And it's not so hard to prove where this inverse formula coming from. Because if I multiply, let's say, H inverse by H, it's like what? It's like R transpose, negative R transpose D, 0, 0, 0, 1 times R D 0, 0, 0, 1. Correct? If I do that, then it is going to be R transpose R. This guy is going to be R transpose R, which is this one times this one. And then plus these two multiplied, which is going to be what? Minus, or sorry, not that one, this one. The first row times the first row, second column, really, or fourth column. So this is going to be R transpose R minus R transpose D times 1. Then here you will get all these zeros times R, correct? And plus 1 times 0, which is going to be 0, 0, 0. And then you will get all the zeros times D plus 1 times 1, which is 1. So let me make sure I did everything right. Oh, yes, I did something wrong. I had to multiply R transpose by this guy, by D, and then negative R transpose D by 1, correct? First row times that column. So this is D, not R. And what would you get now? R transpose is going to be I. This is R transpose D minus R transpose D is going to be 0, a 0 of 3 by 1. This whole thing, you can write it as 0, 1 by 3. And this is going to be a 1. And this is I 3 by 3. So if you look at it, it is going to be I 4 by 4. And when the product of two things, and you can show it if you reverse the order like this, the result is still going to be I. And you know when the result of product of left and right of two matrices is I, those two matrices are what? Inverse of each other, okay? So if you want to invert your homogeneous transformation, the R portion of it will be transposed, no problem. But the D part of it, you have to negate it and multiply it by the R transpose to invert it back. Okay? You have to do that. And you might say, well, what's the meaning of this negative R transpose D? So let me tell you the meaning of that fast too. Because this is clear. R transpose means undo the rotation. Go back, go backwards. But what about this? So what I have here is this one. I have these frames, and the D I have, so this is frame 0. The D that I had was D10, so it was this vector. Origin of 1 with respect to 0, and then I also had an R of 1 with respect to 0 that is shown here. Now, when I want to invert it, what does that mean? It means instead of R10, I have to use R01, which is clearly the transpose of that. But then I have to use this vector, which is d of 0 in 1. Now, what relation exists between these two vectors? Well, you might say they are the negative of each other. That's right, except for one difference. If you look at the way the frame they are written with respect to the reference, this guy is written in frame 1, this guy is written in frame 0. And although this negative thing is absolutely right, but the references are not the same. Remember, in an equation, everything has to be written in the same frame. That's why you have to multiply by what? By R 10 transpose. What does this one do? Well, it is going to be negative of R10 transpose means R01 times D10. Do you see what's happening? It takes this vector that is written in frame 0 and projects it back into what? Frame 1. So the result of this is going to be this guy, but with a negative sign, and now both of them are going to be written in the same frame. So the only reason that you add this transpose is to make sure both of the results are written in the same frame, frame 1. Okay, that's why you have this extra term. And again, H is not a it's not an orthogonal or normal matrix. Good. So this is how we combine them together. And finally, there are some MATLAB commands relevant for this thing. If you look here in this table of MATLAB commands I showed you that you can convert Euler angles to rotation matrix and so on and so forth and everything, right? But for each one of them, you can also convert them to a T form. You see, axis angle to T form, Euler to T form, rotation matrix to T form. Okay, so this T form is very powerful thing, and that's your homogeneous. So let me show you one of them. So rotation matrix to T form. Okay, so it converts your rotation matrix into a homogeneous. So if you pass it, what it does, it forms a 4 by 4, and then in the R portion of it, it fills it with the R that you gave it. Correct? So that's what it does. It forms it with T form, and it can do backwards too. If you have a 4 by 4 rotation homogeneous matrix, it can extract the 3 by 3 first portion of it and give you the rotation matrix. Okay, so that's all it is. But again, you can always do stuff that are more exciting by writing your own code instead of just using the built-in functions that have limitations. And here, before we end this video, I can show you one simple example. So if you remember, I showed you this code where I brought this STL file and manipulated it. Now, here I did it with the rotation of Euler angles. I formed a rotation matrix, I multiplied it, and I could rotate it in place, if you remember, right? Here, I have 90 degrees of psi, 90 degrees of theta, as you can see. Now, not only I want to do these rotations, I want to add the translation as well. Okay, so not only I rotate it, I want to also move the origin of it. So for that, I have to form the H matrix. Okay, so this is my R matrix. Now I have to come up with an H. So I have to say H is what? Is whatever R is plus the displacement vector, and then 3 zeros and a 1. Okay, if I can do it, it means I have formed my H. So this is already a 3 by 3, so all I need is now to define a D. So along which axis do you want to move it, X, Y, or Z? Let's say right now, all I want is to shift it up, only Z displacement. So no X, no Y, and let's say 3 units, or let's say 10 units Z, or 5 units Z. Good, right? Let me make sure if that is big enough. Let me look at the units. It's not going to show much. Let me make it like 20 units or so. So you see some major displacement. Good, so that is my H matrix. I got it. Good, now when I want to multiply it by this vector here, the thing is this vector, this is a 4x4, but this vector was, as you can see, it is like 10,000 points by 3. Remember, what we need is to augment every point by an extra 1 to form the homogeneous coordinate. So right now, if this is 10,000 by 3, I have to make it 10,000 by 4, and the fourth column should be all 1s, right? So what I can do is to come up here and say was is, you see, it has so many points and 3 columns. I say augment a column of all 1s at the end of it. So it has to be 1s of what? As many rows as was have, which is size of was and 1, and then 1 column. So here it is going to be a bunch of 1s. How many of them? 10,000 something by 1. So it's going to be a column of 10,000 1s. You add it on the right side. You see I used space, not semicolon. So it's going to be added to the right side, not below. So here I make it homogeneous coordinate for was, and now I can transpose it. And instead of multiplying it by r, I multiply it by what? By h. So this was v is the transform version of was, but it is in homogeneous coordinates. When you want to pass it to the patch command, you have to get rid of all of those 1s, because the patch command only wants x, y, and z, not extra 1s. So this was v, now the dimension of it is going to be what? It is going to be a 4x4 times a 4 by 10,000. So it's going to be 4 by 10,000. And all we really need is, if you transpose it, which is going to be 10,000 by 4, to get rid of the last column. Okay, or we can get rid of the last row here, so just say rows 1 to 3, correct? And all columns. So this means get rid of the 1s, and then you have to transpose it to make sure the dimensions work. Okay, so now this one hopefully will do the 2 Euler rotations plus a 20 units upward displacement. Now here I got an error. Let me make sure why the error is coming from. It says, yeah, there is a typo. I should have said transpose, I said transpose. Okay, so I guess that's here. Just a small typo. There we go. Now let's see it from the side, see if you can see the effect. This come up, but not so visibly. Let me change this to some bigger number. See if that makes any difference. Well, it doesn't. That is not good. Okay, why is that? Okay, I found the reason. The reason was here, I multiplied H transpose by was, not H. Okay, and it's H that you have to multiply. H transpose doesn't really mean anything. It's not even H inverse. It's H transpose. So now that everything is right, now you can see clearly that you're going up like this, correct? And if you want, you can also move it along the y direction, let's say also 50 units, and do it. And here I changed my angles to like 60 degrees and 45 degrees. If you want, I can put them back to 90 degrees. Shouldn't make much of a difference. Okay, so here, you see the 2 rotations, precision and nutation, both 90 degrees. And then you clearly see a displacement upward in the z and a displacement y on the right side. Okay, so this is called rigid body transformation, and you can go from any position and orientation to any other position and orientation. Okay, so hopefully the video was useful. I'll see you in the next lecture.